Hello everyone, welcome back to another video. And in this video, we're going to be taking a look at a question from the IB Chemistry Paper 2 HL from the May 2018 batch. And this is from Time Zone 1. And even though this is from an HL paper, it shares content with both HL and SL, as you can probably tell. Now, the other day, I put out a post on my Instagram where I asked you guys, which topics do you find most difficult in the IB Chemistry syllabus? And an overwhelming majority of people who commented said topic 1, and there were a few topic 8s and topic 5s, but majority of the people who commented said topic 1, which is stoichiometry. And as a May 2021 student who has very recently graduated from the IB, or will graduate in a week from now when I get my results, but I totally understand where you're coming from. I absolutely despised the topic stoichiometry when I first started IB chemistry as well, mainly because I wasn't very good at math. But as I progressed in the syllabus, I began to realize that it is actually the easiest topic, one, and two, it is the most important topic that you need to know if you want to be successful in chemistry because it is applied everywhere. Every topic, you will find something to do with stoichiometry in that topic, and that is a guarantee. And you've probably noticed this as well. So, hopefully, with this video and many other videos that I've made in the past regarding stoichiometry, I can help to clear away the difficulty that you face in this topic. Now, in this question, they're asking us, urea can be made by reacting potassium cyanate, KNCO, with ammonium chloride, NH4Cl. And they've given us the equation, the word equation, or the chemical equation over here. And the first thing when you are given such a question is that you need to make sure that the equation that they've given you is balanced. Now, sometimes IB balances it, sometimes they don't. That's just how they are. So it's better to be safe than sorry and to just make sure that what they have given you is balanced. So I'm going to check that over here. And by the way, this is ammonia if you didn't get that. So this is ammonia. Sorry, not ammonia. I mean urea, not ammonia. My bad. All right, so is this balanced? Let's see how many potassiums do we have on this side? We have one. What about this side? We have one. What about nitrogen? How many nitrogens do we have on the reactants side? For nitrogen, we have two nitrogens. What about on this side? Over here, we also have two nitrogens. Let's take a look at carbon. How many carbons do we have? Over here, we have one carbon. And over here, we also have one carbon. Sorry. What about hydrogen? How many hydrogens do we have? Okay. On the reactants side, we have 4 hydrogens. And on the products side, we also have 4 hydrogens because it's H2 times 2 because there's 2 H2. So we have 4 hydrogens. And last but not least, we have oxygen and chlorine as well. So how many oxygens do we have? We have 1 oxygen and we have 1 oxygen here as well. And last but not least, we have chlorine. We have 1 chlorine on the reactant side and 1 chlorine on the product side. All right, so, okay, we checked it. It's balanced. Now we can go ahead with the question. And of course, what I have done over here takes a bit longer, but when you get a good practice of how to balance equations, you can do this in your mind in a few seconds itself. Now, why do I do this? Why do I stress the importance of balancing the equation? Why is it important? It's because when they ask you such a question, where they're asking you in this question to figure out the maximum mass of urea that can be formed from 50 centimeters cubed of 0.100 mole dm of potassium cyanate solution. So when they give you such a question, they're asking you to determine in indirectly, they're asking you to first find out the number of moles of urea that is going to be produced from this much potassium cyanate. Now, if you want to find out the accurate number of moles, you need to make sure that your molar ratios, which are these numbers that usually come, or well, don't come in this case, in the behind reactants and products. So for example, you could have some reaction like 2HCl plus NH3 gives, I don't know, 2NH4Cl. I don't know. This is just something that I made up right now. So these twos or these numbers behind, in this case, there is just a 1. We don't write the 1, but it's there. So these give us the ratios. This tells us how much of one product or one reactant is going to be present in this reaction based on these molar ratios. So for example, if I have, suppose, substance A, if I have A to A plus B is going to give me A to B. This is just some random reaction with random letters. So if we have such a uh, reaction, and I tell you that we have 0.5 moles of A, how many moles of A to B can we produce? The maximum amount of moles? Well, we just have to halve the number of moles of A to find out the amount of A to be produced. And that's because, look at the ratio, it's 2 to the 1. Remember, we don't write the 1, so but it's just there. 2 to 1. So that means that for every 2 moles of A used, we're going to only produce 1 mole of A to B. So half of that. So if we were to determine how many moles of A to B is going to be produced based on the fact that we have only 0.5 moles of A, we are going to be write 0.25, because based on this equation, that is the molar ratio. And you must be wondering, what about B? Well, we can say that B is considered as the excess reactant. It is in excess, so there is no limit to how much there is of B in the reaction. So you can use as much of it as possible. Example. But A is the one that is in limit. It is the one that determines the maximum amount of A to B that is possible to be gained from this reaction. And it's a very similar case in the question as well, where they have told us that KNCO, potassium cyanate, is of a certain quantity. We have to determine the moles. And then out from that, we have to determine how much urea can be formed using this information. And I'm going to show you how to do that. So like I said, the first thing we need to do is find the number of moles of urea that can be produced. And in order to find out the number of moles of urea that can be produced, we need to first find out the number of moles of potassium cyanate that is being used. So they've told us that we have 50 centimeters cube of 0.1 mole DM potassium cyanate solution. So how do we find the number of moles? Well, for this, the formula is number of moles is equal to concentration times volume, and volume is in DM cubed. So we know what the concentration is. We know that the concentration is 0.1. And we also know what the volume is, but we know what the volume is in centimeters cube. Now, if you want to convert from centimeters cube to DM cube, you have to divide centimeters cube by 1,000. So 50 centimeters cube divided by 1,000 is going to give you your answer of volume in DM cube. So basically, number of moles would be 0.1 times 0.05. And that gives us an answer of, let's check it out. How much would that give us? Of 5 times 10 to the negative 3 moles of potassium cyanate. So we have these many moles of potassium cyanate, of KCNO. That's how many moles of potassium cyanate we have. Now, what do we do next? We need to now find out the number of moles of urea. And based on this chemical equation that they have given us over here, based on this and looking at the molar ratios, we can tell that potassium cyanate and urea are in the 1-to-1 ratio. That means if you produce if you use 1 mole of potassium cyanate, you're going to produce 1 mole of urea. If you use 2 moles of potassium cyanate, you produce 2 moles of urea. Likewise, but just imagine for a second that this was 2 KNCO. Now, this is completely wrong, but I'm just giving you a hypothetical situation. Imagine this is correct. Now, if this was the case, the ratio would become 2-to-1. So that would mean if I'm using 2 moles of potassium cyanate, I will only produce 1 mole of urea, so half of what I'm using. Whereas if this was the case, if it was this, where there was a 2 for urea, that would mean for every 1 mole of potassium cyanate that I use, I'm going to produce 2 moles of urea, so double of what I use. And hopefully that makes sense to you. This is basically why we balance the equations, to get the molar ratios and to make sure that they're correct. But however, in this case, as I said earlier, all the substances are in the 1-to-1 ratio. So for every 1 mole of potassium cyanate I use, I'm going to produce 1 mole of urea. So if I use 5 times 10 to the power of -3 moles of potassium cyanate, I'm also going to produce 5 times 10 to the power of -3 moles of urea. So we found out the number of moles of urea that will be produced based on the number of moles of potassium cyanate. But in this question, they've asked us the maximum mass of urea that is going to be formed. Now, over here, you will have to play along, or you have to play a bit or manipulate an equation. And I'm going to show you. I'm sure many of you might already know what I'm talking about, but if you don't, let me show you. When we calculate the number of moles for a substance, or at least for a solid substance, for a substance which has mass, which you can measure the mass of. I'm not talking about a liquid or a solution. I'm talking about a solid substance which has a mass. We use this formula. So number of moles is equal to the mass of the substance in grams divided by its molar mass. Now we need to find out the number of moles, or sorry, the mass of urea that is produced, right? And we know already what the moles of urea that is going to be produced is. We know that it is 5 times 10 to the power of -3 based on the information we gathered earlier. We also know the molar mass of urea, which is 60.06. If you're confused about how I got this, you just have to basically add up the relative molecular masses of all the elements used and the number of elements that there are in urea. I'm sure all of you know how to calculate the molecular mass of a substance. So this is the molar mass of of urea. And now we have to find out what is the mass in grams. And as you can probably tell, we have to now rearrange this equation. So we take this to the other side. So we multiply this side by 60.06. These cancel out. But remember, we also do the same to the other side. We also multiply this side by 60 times 0.6. So basically, our mass in grams is equal to 5 times 10 to the power of -3 times 60.06. And if you put that into your calculator, this is a paper too, so you have access to your calculator, you should get the answer of around 0.3003 grams of urea. So that is the maximum mass of urea that you can obtain by using 50 centimeters cubed of 0.1 mole DM potassium cyanate solution. So that is your answer. Hopefully that has all made sense. I know it is a challenging concept to both explain and to understand, but hopefully I have been clear. Thank you so much for watching this video. If you have any other questions regarding this concept or any other concepts, please feel free to let me know in the comments, send me an email or message me on my social media, and I'll be more than happy to help you. Thanks a lot. I'll see you in another video with another question. Goodbye.